Good day everyone, welcome to another tutorial by M.I.B. Math is Beautiful, and today we'll be looking at proof by contradiction. Now proof by contradiction is a form of indirect proof where you show that the negation of the proposition in question is actually false. Hence the proposition itself has to be true. Now you simply do this by assuming the negation of the proposition, then prove that the negation itself leads to a contradiction. Let us assume a proposition P. The first step to do is that you assume that P is false. Therefore, not P is true. And then the second thing to do is basically using the proof to show that not P implies P, which in itself is a contradiction. Hence, the original proposition P has to be true. Now let us look at an actual question. Now let us consider this question here. If A and B are elements of Z, which is an integer, then A squared minus 4B is not equal to 2. The first thing to do is assume the negation is true. So the assumption for this question would be if A and B are elements of Z, then A squared minus 4B is actually equal to 2. The second step is to use the proof to show that the negation of the proposition implies the proposition. Therefore, the proposition itself must be true. And this is done by simply working out the question. So we assume the negation is true, so A squared minus 4B is equal to 2. A squared is equals to 4B plus 2, which is actually 2 times 2B plus 1 upon simplification. Upon factorizing this equation here. So A squared is actually even, right? Because A squared is equals to 2 times an integer, which is 2B plus 1. Remember that even numbers are of the form 2 times k, where k is an integer. In this case, k would have been represented by this here, 2b plus 1. Now, if A squared is even, then A is also even, right? Now let us denote A using another integer, using another even integer as 2c. Now, substituting A equals 2c in the negation, we will actually get 2c squared minus 4b is equals to 2. So 4c squared minus 4b is equals to 2. Now factorizing, we'll get 4 times c squared minus b is equals to 2. Right? Simplifying this, we can actually get 2 times c squared minus b is equal to 1. Now, looking at this here, we can see that 2 times c squared minus b is actually even, right? Now, because an even number is denoted by 2 times an integer, where the integer here would have been c squared minus b would have been an integer. Now, if this is actually even, this implies that 1 is also even, based on this equation here, 2 times c squared minus b equals 1. But we know that 1 is not an even number, therefore leading to a contradiction, right? So this implies that the original proposition itself must be true, and that if A and B are elements of Z, then A squared minus 4B cannot be equal to 2. Question excellently done. Math is beautiful. Now let us consider another question. Suppose a, which is an element of z, an integer, and a squared is even, then a is even. So first things first is the assumption, and the assumption is that if a is an element of z and a is even, then a is odd. Correct? Now, if a is actually odd, assuming n being an integer, a will actually be in the form of 2n plus 1. Right? Now, if that is the case, therefore, a squared would be equal to 2n plus 1 all squared. So a squared is actually equal to 4n squared plus 4n plus 1. A squared would be equal to 2n squared plus 2n plus 1. And as you can see, this here is odd because this is in the form of an odd number, which is 2n plus 1, where n is an integer, and in this case 2n squared plus 2n squared plus 2n coming from here would be equivalent to what n is in as an integer in the odd formula of 2n plus 1, right? So therefore this is saying that a squared is actually odd. So a squared is odd. However, in the assumption, a squared is even, which is what? A contradiction. Therefore, the supposition a element of z, a squared is even, implies a is even, is true. Right? Question excellently done. Math is beautiful. Thanks for watching this video. Please like, subscribe, hit the notification bell, leave your comments, and visit us on Facebook at M.I.B. Math is Beautiful.